We're looking for the value of P that makes the series to be a convergent series. Here you have the summation of 1 divided by n times ln of n to power P. Let us apply the integral test. Remember that when we talked about the P series in general, or if we have an exponent like P, we applied the integral test. For the integral test, we saw that for a series like an, n starts from 1, goes to infinity, if the function f of n, which is an, f of x, is positive, continuous, and decreasing, then we have the following. If the integral of f of x dx is convergent, then we can conclude that the summation of an, n starts from 1, goes to infinity, is convergent as well. And we saw that if the integral is divergent, the series is a divergent series as well. But let us take a look. For this function here, f of x equals to 1 divided by n times ln of n. To power p, we can assign different values to p and use Desmos and visualize this. For example, if p is equal to 1, you get 1 divided by n times ln of n. And the graph, as we saw before, in previous example, behaved like this. So for p equals to 1, for example, the function behaves like this. It has some asymptotes, but in general, if you want to visualize this guy, it behaves like this. So on the positive part of x-axis, it's like this. And if you want to include the rest of the things, well, it is very similar to this shape. So as you can see, it is positive. We are ignoring this part. Take a look at the domain. The domain that you're looking at is 2 to positive infinity. It is positive, continuous, and based on the graph, it must be a decreasing function. If you plug in p equals to 2, for example, you get the following graph. These are not very accurate, so if you want to see a more accurate graph, I highly encourage you to use Desmos or any other graphing device that you're using. So now if you raise it to power 2, the function behaves like this. So the decreasing part stays the same. And for the other part, you indeed have some vertical asymptotes, and the graph behaves like this. Okay. Do my best to graph it the way that it makes a little bit sense. But again, since you're just looking at the interval 2 to infinity, you can ignore this part. This part doesn't count. You only look at this part of the graph, which is indeed positive, continuous, and decreasing. So you can continue this process and check the behavior of the function f of x equals to 1 divided by n times ln of n to power p, right? So it satisfies the integral test. The integral test is satisfied. It is positive indeed, it is continuous indeed, and it is decreasing indeed. So we can apply the integral test. Since the function f of x equals to 1 divided by x times ln of x to power p satisfies all three conditions, so we can apply the integral test. We need to take the integral of this function dx divided by x ln of x to power p, and the boundaries that you're taking the integral over is 2 to infinity. This is a very simple method to calculate the integral. Why is that? If you take u to be ln of x, you already have du, which is dx divided by x. You already have your du here, and this is your u. So this integral in turns can be written as the integral of du divided by u to power p. Remember, from calculus, if you have the integral of u to power n du, this is equal to u to power n plus 1 divided by n plus 1 plus constant of integration. So this integral in turns can be written as the integral of u to power negative p du, which is equal to u to power 1 minus p divided by 1 minus p. But what is our u? The u itself is ln of x. So you have ln of x to power 1 minus p divided by 1 minus p as your x ranges between 2 to infinity. Now our job is to analyze ln of x to power 1 minus p. So since ln function, the behavior of ln function is like this. If you have ln of x in general, if you go to infinity, the ln goes to infinity as well, right? Basically on y-axis. So if you plug in infinity into your ln function, and if this exponent makes it positive, then it is going to be infinity. So let us write this down. Since the limit of ln of a quantity like x, as x goes to infinity, is infinity, so our ln of x to power 1 minus p must land on the denominator. Because if it's on the denominator, then 1 divided by infinity becomes 0. So 1 over infinity becomes 0. For the ln of x to power 1 minus p to be on the denominator, 1 minus p must be a negative value. Okay, it was easy. 1 minus p must be negative. P must be more than 1. So for any p value, more than 1, the series of the form of the summation of 1 divided by n times ln of n to power p, n starts from 2 to infinity, is a convergent series. So this is our answer. This is what you're looking for. Let us recap what we did so far. The question says, find a value of P that makes the series to be a convergent series. This is the series that we have, the summation of 1 divided by n times ln of n to power p, and starts from 2 to infinity. We can apply integral test here. Why is that? Because function f of x, 1 divided by, let me write everything in x to avoid any confusion when you're rewatching this, ln of x to power p, it's always positive, continuous, and decreasing. What we did, we plugged in some values for p and analyzed the behavior of the function itself. So since you're looking at the interval 2 to infinity, you are looking at the positive part of the graph. You can ignore this part of the graph when p is equal to 1. So obviously, the function is positive, continuous, decreasing. If you plug in p equals to 2, again, you can ignore this part of the graph because you are on the interval 2 to infinity, and the function is positive, continuous, and decreasing. You can plug in other p values if you want to, and then use Desmos, p equals to 3, any other value, and analyze the behavior of this function. Indeed, the function is positive, continuous, decreasing on the interval 2 to infinity. So now we can apply the integral test for the function f of x equals to 1 divided by x times ln of x to power p. The integral test says, hey, the integral, if the integral is convergent, the series is convergent as well. We already know how to analyze an integral. The integral of dx divided by x times ln of x to power p, x ranges between 2 infinity, can be evaluated using a simple substitution method. U is ln of x, du is dx divided by x, so you can convert this integral into du divided by u to power p. But from calculus, remember that the integral of u to the n, du is u to n plus 1 divided by n plus 1. So basically, this integral becomes u to power 1 minus p divided by 1 minus p, but u is equal to ln of x. So substitute this guy here, you get ln of x to power 1 minus p divided by 1 minus p. We are stopping at this time and looking at the behavior of our ln function. Ln function behave the way that when x goes to infinity, your function goes to infinity as well. But if it is on the denominator, the limit of ln of x as x goes to infinity becomes 1 over infinity or 0. So our goal is to have ln of x to power 1 minus p on the denominator. How this guy land on the denominator? If it has a negative exponent. If this exponent here is negative, then this quantity lands on the denominator. So 1 minus p must be less than 0, or p must be more than 1. So as long as p is more than 1, the series is going to be a convergent series.